So the title of my presentation is the structure-activity relationship of carbazole benzylpiperidine multi-targeted ligands in relation to acetylcholine esterase inhibition. So the goal of this paper was to synthesize a series of novel carbazole benzylpiperidine multi-targeted ligands for the treatment of Alzheimer's by fusing donepezil and beta-secretase together. Biological activity of the compounds were tested through a variety of in vitro assays, such as inhibition studies on acetylcholine esterase, inhibition studies on butyrylcholine esterase, kinetic studies on acetylcholine esterase and butyrylcholine esterase inhibition, a beta-secretase assay, metal chelating assay, and docking studies. So, what is Alzheimer's disease? Alzheimer's disease is the most common form of dementia among the elderly, and it's a neurological illness characterized by loss of brain function affecting memory, cognition, and behavior. So this is just a little refresher of what the exact causes of Alzheimer's disease are. So basically, there are several causes of Alzheimer's disease, such as beta amyloid aggregation, high levels of oxidative stress, low levels of acetylcholine and butyrylcholine, and dyshomeostasis of biometals in the brain. Out of all these causes mentioned, scientists believe the most important cause of Alzheimer's disease is due to low levels of acetylcholine, which is due to the hydrolysis of acetylcholine catalyzed by the enzyme acetylcholine esterase. Since similar to my last presentation, which focused on acetylcholine esterase inhibition, this presentation will also be focusing on the synthesis of the multi-targeted ligands that will act as inhibitors of acetylcholine esterase, which will prevent the hydrolysis of acetylcholine and hopefully increase the levels of acetylcholine in the brain. And on the side, I know I explained this diagram last time, but I'll just explain it again. There's a diagram of the enzyme acetylcholine esterase, and basically the hydrolysis of acetylcholine is shown here. Acetylcholine is basically broken down by acetylcholine esterase in the synaptic cleft, and choline is then transported back to the axon terminal and is used to produce more acetylcholine. So shown here is compound 4U, which was the most potent and efficient compound synthesized against acetylcholine esterase inhibition in my previous paper that I did. The donepezil moiety, which is specifically the N-benzylpiperidine from donepezil, is highlighted in blue. The donepezil moiety acts as an acetylcholine esterase inhibitor and binds to the catalytic site of acetylcholine esterase. The melatonin moiety, specifically the indole, is highlighted in red and exhibits antioxidant and anti-AB aggregation properties, which is also binding to the peripheral and anionic site of acetylcholine esterase. The carboxamine linker present, which is highlighted in green, was used to link donepezil and melatonin together. In my previous presentation, we observed that there was a direct relationship between the linker length of the multi-targeted ligand synthesized and acetylcholine esterase inhibition. As the linker length increased, inhibition of acetylcholine esterase increased, making compound 4U the most potent at inhibiting acetylcholine esterase since it contained the greatest linker of two carbon spacers. So I believe that the carbon spacers lead to an increase in activity because this allows the benzene moiety of donepezil to reach the active binding site of acetylcholine esterase and interact with amino acid residues through van der Waals forces. This leads to an overall increase in inhibition of acetylcholine esterase. So now I will be talking about the molecules that were fused together in my current paper to create the novel carbazole benzylpiperidine ligands. So this is the structure of donepezil, and the highlighted part of donepezil in blue will be the part used in the multi-target ligands. Donepezil is recognized by the acetylcholine esterase active site by interactions with the benzyl moiety, which binds to the catalytic and anionic site of acetylcholine esterase, the atom of the piperidine, and the dimethoxyindodone moiety, which binds to the peripheral anionic site of acetylcholine esterase. Donepezil also acts as a metal chelating agent. So this is the structure of beta-secretase, and the highlighted red portion of beta-secretase, which is called carbazole, is what will be used in the multi-target ligands. Carbazole is a tricyclic structure with various biological activities related to Alzheimer's disease that previously have shown to have, anti-Alzheimer's properties, such as neuroprotective properties, anti-acetylcholine esterase properties, anti-amyloid beta aggregation properties, and anti-butyrylcholine esterase and antioxidative activity. The carbazole has also been reported to exhibit metal chelating properties. So shown here is the carbazole benzyl piperidine multi-target ligand synthesized in the paper using the various linkers. As you can see, the carbazole part of the hybrid, which is highlighted in red, exhibits antioxidant properties and anti-amyloid beta aggregation properties and anti-butyrylcholine esterase properties. It's ideal that multi-target ligands would have antioxidant properties because one of the causes of Alzheimer's disease is high levels of oxidative stress. Carbazole having antioxidant properties will react with the free radicals produced in our brain from energy production to decrease the levels of oxidative stress experienced. The carbazole moiety also exhibits anti-amyloid beta aggregation properties, which will help prevent amyloid buildup in the brain, which is also a cause of Alzheimer's disease. So also in addition to this, the carbazole moiety also has anti-butyrylcholine esterase properties, which is essential in order to prevent the hydrolysis of butyrylcholine by butyrylcholine esterase and obstruct the low levels of butyrylcholine. The donepezil moiety, which is highlighted in blue, acts as an acetylcholine esterase inhibitor, which is essential to Alzheimer's disease prevention, since the main cause of Alzheimer's disease is low levels of acetylcholine in the brain. Overall, the multi-target ligand will act as an acetylcholine esterase inhibitor and will prevent acetylcholine esterase from hydrolyzing acetylcholine. Both the carbazole moiety and donepezil exhibit metal chelating properties. This is also important because going back to my previous slide, this homeostasis of metal ions also was a contribution to Alzheimer's disease. Metal chelation is important as this will prevent metals from binding to the amyloid beta and tau proteins in the brain and allow them to dissolve normally. Also, donepezil, specifically the N-benzyl piperidine, binds to the catalytic and ionic site of acetylcholine esterase through pi-pi aromatic stacking, and the carbazole moiety of beta secretase binds to the peripheral and ionic site of acetylcholine esterase also through pi-pi aromatic stacking. This makes the multi-target ligand synthesized dual binding inhibitors. The two fragments were fused together through a variety of linkers, which will be shown in black. So comparing the multi-target ligands that I previously talked about and these novel carbazole benzyl piperidine multi-target ligands, donepezil, specifically the N-benzyl piperidine moiety of donepezil, was used in both the multi-target ligands I've discussed. However, in my previous paper, melatonin was used, and now the carbazole moiety from beta secretase is being used. So looking at these structures, it's observed that melatonin and beta secretase both have similar backbone structures containing the phenyl ring and the five-membered ring, and they both contain amide groups. Along with the physical similarities, both of these compounds also exhibit similar biological activities, such as antioxidative and anti-amyloid beta aggregation properties and metal chelating properties, and they both bind to the peripheral and anionic site of acetylcholine esterase through pi-pi aromatic stacking interactions. So I think it was really interesting to see how similar these compounds were, even though they were different, and they also exhibited similar biological properties and have similar structures. So now I'm going to be talking about the in vitro acetylcholine esterase inhibition that was performed. So it was observed that between compounds 9B and 9C, that compound 9B exhibited greater inhibition of acetylcholine esterase, having a lower IC50 value of 16.5 micromolar. Compound 9C had an IC50 value of 26 micromolar, which is larger than the IC50 value of the compound 9B, therefore making compound 9B slightly less potent and efficient at inhibition of acetylcholine esterase. The difference between compounds 9B and 9C is that compound 9B has an amine linker containing 5 carbon spacers, while compound 9C contains an amine linker with 6 carbon spacers. Therefore, it can be observed that in this paper, as the linker length increases, the inhibition of acetylcholine esterase will decrease. This is completely opposite from the relationship observed in my previous paper, which determined that a longer linker length led to an increase in acetylcholine esterase inhibition, in which compound 4U, which is shown here, exhibited the greatest inhibition of acetylcholine esterase with a 2-carbon spacer linker length. So the last paper I focused on didn't really test a variety of different linker lengths. They tested linker lengths having 0 carbon spacers or 2 carbon spacers, and in which the compound having 2 carbon spacers showed the greatest inhibition. So I believe that if they were to actually test compound 4U with having an increasing number of carbon spacers, they would come to the same conclusion as the researchers in this current paper came to, which is that an increase in linker length leads to a decrease in acetylcholine esterase inhibition. So as the pocket of acetylcholine esterase is deep, a few carbon chains as a linker are needed at the middle site between the gorge and the entrance of acetylcholine esterase. So therefore, I believe the linker has to be a suitable fit, long enough in order to allow the donepezol moiety and the carbazole moiety to bind to the catalytic anionic site and peripheral anionic site of acetylcholine esterase through pi-pi interactions, but not too long, in which the molecules cannot reach their designated active sites due to excessive bulkiness and largeness of the molecule because of an increase in linker length. Especially looking at the carbazole moiety, it's already sterically bulky. There's a lot of rings compared to the melatonin moiety stacked onto it. So I do believe a smaller linker length would definitely allow the molecules to reach their designated active sites perfectly. So multi-target ligands 9G and 9I were synthesized as well, in which compounds 9G and 9I exhibited IC50 values of 13.4 micromolar and 26.9 micromolar respectively. It is also important to know that compound 9G exhibited the greatest inhibitory activity of acetylcholine esterase out of all the compounds synthesized by the researchers, and therefore had the lowest IC50 value, while compound 9I exhibited a higher IC50 value of 26.9 micromolar, making it a weaker inhibitor of acetylcholine esterase. So both compounds contain acyl linkers. The difference in compounds 9G and 9I can be seen within their linker lengths. Compound 9G has an amine present within its linker, and compound 9I has no amine present within its linker length. Compound 9G also contains a smaller linker length of 3 carbon spacers, while compound 9I contains a linker of 4 carbon spacers. As seen before, an increased length in carbon spacers leads to a decrease in acetylcholine esterase inhibitory activity, making the overall multi-target ligand too large to reach into the deep pockets of acetylcholine esterase, and therefore preventing potent inhibition of acetylcholine esterase, since it has a longer linker length. So it makes sense why compound 9I didn't give as great inhibition of acetylcholine esterase as compared to compound 9G. Also, in relation to the protonated nitrogen present within the linker length in compound 9G, the protonated nitrogen atom in the linker forms cation pi interactions with amino acid residues and hydrogen interactions with amino acid residues in the middle of the active gorge. Compound 9G is therefore stabilized by not only pi-pi stacking interactions, but also cation-pi interactions with amino acid residues and hydrogen bonding interactions, which further leads to compounds 9G stabilization and conformation within the active site of acetylcholine esterase. Also, since compound 9G contains a 3 carbon spacer linker length, which is suitable enough, meaning that it's not too large enough or too small to fit into the deep pocket of acetylcholine esterase, where the carbazole moiety and the N-benzyl piperidine moiety can bind to their designated sites through pi-pi stacking interactions. So shown here is compound 4U, which was the multi-target ligand synthesized in the previous paper studied, and this compound exhibited the greatest inhibition of acetylcholine esterase, having an IC50 value of 0.193 micromolar. Compound 9G had an IC50 value of 13.4 micromolar. So both of these compounds exhibited the greatest inhibition overall of acetylcholine esterase. They are both extremely similar in structure, in which both of these compounds contain the N-benzyl piperidine moiety and protonated nitrogen within their linkers. The structure of the melatonin moiety and carboxyl moiety are also very similar to one another, containing similar backbone structures of the phenyl ring and the 5-member rings. I believe both of these structures exhibited the greatest inhibition of acetylcholine esterase because both of these compounds are able to participate in pi-pi aromatic stacking with the catalytic anionic site of acetylcholine esterase through the donepezil moiety. Both of these compounds actively participate in pi-pi aromatic stacking and cation-pi interactions with the peripheral site and ionic site of acetylcholine esterase, and partake in hydrogen bonding interactions with amino acid residues within the active site of acetylcholine esterase. Compounds 4U and 9G are able to create these stabilizing interactions because they are able to suitably fit into the deep pocket of acetylcholine esterase due to their small linker length, which allows the donepezil moiety and melatonin and carboxyl moiety to reach their active sites to bind to their designated sites. So I believe the exceptional stabilization and conformation of these molecules in the pocket of acetylcholine esterase through such interactions can be held accountable for why these two compounds exhibited the greatest acetylcholine esterase inhibition out of both papers. So after reading both of these papers, I've proposed new compounds. So the current paper didn't really discuss adding electron substituents to the multi-targeted ligands like my previous paper mentioned. So with the idea of improving and optimizing compound 9G, I have decided to add electronic substituents to the ortho, meta, and para positions, and to see if the addition of an electron donating substituent will help increase inhibition in acetylcholine esterase, similarly like how it did in the previous paper I discussed. So in compounds 1, 2, and 3, I've decided to add a strong electron donating amine group to the ortho, meta, and para position of the benzene ring of donepezil. So I believe that this addition of a strong electron donating group placed on the benzene moiety, along with the increased linker length, would further increase inhibition of acetylcholine esterase by leading to an increase in donation of electrons to the aromatic ring, which would lead to a larger decrease in repulsive interactions between the aromatic rings of the inhibitors and the amino acid residues in the active site of acetylcholine esterase. So I suspect that along with the addition of a strong electron donating group, a small linker length containing 3 carbon spacers would contribute to the inhibition activity of acetylcholine esterase by increasing the length of the molecule as a whole and allowing the molecule to reach into the deep pocket of acetylcholine esterase, in which the donepezil moiety and carboxyl moiety will reach the peripheral anionic site and catalytic anionic site of acetylcholine esterase, and therefore participate in van der Waals interactions while not being too large. I also believe that using a linker length containing the protonated nitrogen would offer the best stability and efficiency of the following molecules towards acetylcholine esterase inhibition. Since the nitrogen will form cation-pi interactions with amino acid residues and hydrogen interactions with amino acid residues as well in the middle of the active gorge, which adds extra stability. So compounds 4, 5, and 6 contain strong electron withdrawing cyanide substituents on the benzene moiety of the multi-target ligands proposed in the ortho, meta, and para position. In addition to this, the linker length of compounds 4, 5, and 6 also contain 3 carbon spacers from compounds 9G. So following the trend observed involving the electron donating groups and electron withdrawing groups from my previous paper, I believe that compounds 4, 5, and 6 will exhibit moderate to weak inhibition of acetylcholine esterase. activity if an acetylcholine esterase inhibition assay was performed, even if the reduced linker length is present. This is due to the fact that the cyano electron withdrawing group will reduce the electron density around the aromatic ring and therefore reduce the strength of pi-pi interactions that take place between the enzyme inhibitor complexes. And I also believe that the small linker length of 3 carbon spacers will help carbons 4, 5, and 6 get into the acetylcholine esterase pocket to interact with the peripheral anionic site and catalytic anionic site, the binding sites, and the protonated nitrogen will able to form like stabilized interactions. But like I also believe that the electron withdrawing substituents will overpower the ligand's ability to effectively interact with the acetylcholine esterase peripheral anionic site and catalytic anionic site, and therefore will result in weak inhibition. So like I believe like the molecule like will be able to like get in there and fit in there, but overall I think the electron withdrawing group will overpower the ability of the multi-target ligand to bind to its designated active sites because it's so strong. So in conclusion, a series of novel carbazole benzopyperidine hybrids as multifunction agents for the treatment of Alzheimer's disease was synthesized, and the synthesized compound N-benzopyperidine moiety was attached to the carbazole fragment by various linkers. It was revealed that compounds 9B, 9C, and 9G exhibited promising inhibition against acetylcholine esterase. The results suggest that these synthesized compounds would be candidates for the development as multifunctional drugs in the treatment of Alzheimer's disease.